Good morning, everyone. And we'll just flick screens. Oh, there we go. Beautiful. So welcome to the presentation this morning. I'm going to give you a little bit of a different perspective on what systems engineering looks like to me throughout my career. And I have had two very different applications of systems engineering, as you'll see. So I'd like to begin by acknowledging the Wurundjeri people of the Kulin Nation on whose lands we meet today, and pay my respects to elders past and present. And I put these examples up because I strongly believe that systems engineering is not a new concept, although we define it differently today to how our Indigenous communities would define it. So these two examples of Indigenous engineering, the top one is fire management. And it's certainly reflective of many of the criteria that we've just spoken about and that you'll be assessed on in terms of particularly the testing and the validation and the reviewing what's appropriate for a land at a given time, depending on how much rain there's been and what vegetation is present. And the bottom one is one of my favourite examples of Indigenous engineering, and it's a fish trap. What I really like about this particular design is how sustainable it is, not the fish trap itself, but its effect on fish populations. So it's designed so that the smaller fish can actually swim through the trap, and in that way it maintains the population of fish in the system, which from an ecological point of view is really quite amazing when you think of how we fish commercially today and how destructive that process is. So a little bit about my journey and what I've done in my career. So I'm an aerospace and avionics engineer by training. My avionics is predominantly computer science and electronics type subjects. And I was lucky enough when I graduated from RMIT to get a job on site here in Melbourne at the Boeing facility, where we build a whole range of different commercial aircraft components and some military as well. For the 787, which is the program I spent most of my career on, I was at Boeing for 9 years, and we build the movable trailing edge. So when you're flying and you see the bits on the back of the wing that move, they're all built here in Melbourne for the 787. I started as a materials engineer, and I've got some anecdotes and some, I suppose, sharing to share with you today about what the production process for the 787 looks like. So the components we build here in Melbourne, we build from start to finish. The Melbourne site is quite unique. It's the only site outside the US that has design through testing through manufacture, and the componentry that we put in a box here in Melbourne gets bolted straight onto the back of the wing. This is a photo of the production line in Seattle, in Washington, in the States, 478. It's what they designed this system as a plug-and-play system. So the idea was that it was Boeing's first attempt at a truly global production system, where if I just look at the fuselage of this aircraft, it's built in 5 different countries. And the idea was when it came into this factory that it would all just bolt together, like a big jigsaw puzzle, if you like. For the components we build here in Melbourne, and unfortunately it's just off the back of the bottom of this photograph, but for the components we build in Melbourne, the wings are actually sat on crates effectively, and the components that we build here are bolted onto the wing before they're installed on the aircraft. So to give you some examples of what can go wrong in a production system, particularly one of this scale, for the first probably 5 years of production of this aircraft, rather than bolting those components on when the wings were down at eye level, and they are literally at eye level, you can walk up to the back of the wing, we ran late. We ran so late that they had to install the wings on the aircraft, and consequently they're 14 metres in the air, and they had to build unique scaffolding every time that our boxes turned up with the movable trailing edge in them. Needless to say, they were not very happy with us for many years. And occasionally they got dropped or they got bent or damaged. So one of the things about a production system that I think is really worth considering is waste, and it's something I'm very passionate about. It's something you'll see in the media a lot. And again, the aerospace industry provides some large-scale examples of what that can look like. The most common form of waste that we think about is physical things that we have to throw out. And in the context of an aircraft system, when you're starting to build a new aircraft from scratch, to give you an idea of what that waste looks like, each of those aircraft is worth about $250 million. And when we started the production line, we built 12 of those that are all scrap. They're used for testing, they go into the museums, some of them, but they're effectively rubbish. That's a pretty big waste out of a production system. Along the way, other things get damaged. I think the other really strong example of waste in a system like this, and certainly in any system, whether it be an office or your schools, is human waste and the waste that we create in the work that we do. And the best example I can give of that is not only the scaffolding that had to be constructed to build this aircraft, as I spoke about before, but also the travel time associated with building an aircraft like this. So if you're the guy in the middle of the fuselage and there is a guy who crawls around under the floor and tightens up bolts when you're putting bits of the fuselage together, you really do not want to be going to have to pick that bolt up from potentially kilometres away in the factory. You really want that thing to be right next to you when you need it at the time you need it. And that's what a lot of my job was. So I started as a materials engineer at Boeing here in Melbourne, and then I worked for 3 years in our factory as a production manager in the factory. And a lot of our job in the factory was to make sure that the people doing the job had the tools they needed and the materials they needed at the time they needed them in the process. So a couple of examples of what waste can look like in a production system. This is probably one of the most widely known, and I apologise this image is so squished, but this is the 737 production line. It's a different example, and again I spent some time working on the 73 line in Seattle. The thing that's quite unique about this particular line is that it's a moving line. So the aircraft continuously moves, it's bolted onto tracks in the floor, and it slowly makes its way through the factory. To give you the idea of the scale and efficiency that can be achieved for an aircraft that we've been building for nearly 30 years, or just over 30 years now, the 787 we build about 20 a month, 16 to 20 a month, depending on the month. On the 737 line, they make 64 aircraft a month roll off this line, completely painted, ready to fly away. So if you think about that, that's more than 2 every calendar day, and they only work 5 days a week. It's a huge volume of aircraft, and every time I say that, I usually have somebody ask, where are they all going? I don't know, is the short answer. Some of them are used for military purposes, but most of them are commercial 737s. It's one of the most widely flown aircraft in the world. In terms of the engineering and what that looks like to be an engineer on a line like this, it's all about keeping that line moving. Every time that stops, there's losses associated with that for the factory. So the engineering team, and I particularly worked in the production engineering team, whose job it is to problem solve when something unusual or abnormal happens, they have about 4 minutes to respond when this line stops. So they're on 3 shifts a day. There is literally like emergency lights that go off in the factory to tell you where in the line the stoppage has been, and the team has to respond within 4 minutes. So they actually sit down the right-hand side of this photograph in all those booths down the side. That's most of the production engineering team sit down that side of the aircraft. I was saying to the last group that in terms of production processes, and I know that repair and safety and looking at what can go wrong in a process is an important part of the criteria for this subject. The most common repair on the 737, can anyone tell me what you think it might be during the production process? I'd be very surprised if you could guess, but does anyone want to have a crack? So these aircraft are aluminium fuselage. They're a single piece when they come into the factory in Seattle. They're trained in from across the US. They're made in the States, and they're brought in on train carriages covered with tarpaulins. The most common repair in this production system is bullet holes in the fuselage, because they're very obvious, and people take pot shots at them as they're training the fuselage across the country. So, a bit of a random fact. I don't know if anyone will believe you if you share that with them, but I guarantee it's true. So, in terms of what my career looked like and the type of testing we do in a highly complex production system like this, we do everything from the top of this slide, which is materials testing, to the bottom, which is what we call full-scale testing. And I'd encourage you to think about that when you're doing your designs. The top of this slide, Boeing here in Melbourne is the only site outside the US to have ever qualified a material for flight on a commercial aircraft, which was both a good and a bad idea. It means you're very alone because nobody else is using what you're using. And when I started, I spent about 2.5 years in a lab predominantly doing testing like this. So we pulled these things, we wet them, we heated them up, we put them in high humidity environments, we repeatedly pulled them until they broke. We put holes in them, not bullet holes, just drilled holes. We put damaged holes in them. So what happens if you're drilling a hole during the production process and someone gets it slightly wrong? It doesn't look like it should. We put fasteners in them and then pulled them apart, all sorts of different types of tests, and looked at how they failed and at what loads they failed. That information was used by our design team to make sure that when you and I, as members of the flying public, fly on a commercial aircraft, they're so well over-designed that there should never be a failure in flight. The flip side of that is what we call full-scale testing. So I mentioned that the first 12 aircraft are scrap. Of those, 1 or possibly 2 is used for what they call long-term fatigue testing. This is actually the 737 again, because I couldn't find a photo that was released of the 78 for the same test. But all those orange things that you can see in that photograph are weights. It's a fully mechanical test. It's not, there's no people involved in this. But effectively what they do is they take the wings of the aircraft and they bend them up and down and up and down and up and down for literally millions of cycles. The test takes between 8 and 11 years to complete. And the goal is to stay ahead of the airlines. So for an aircraft, when it's sitting on the ground and its wings are full of fuel, the wings droop, and you can see this if next time you fly or next time you're near an airport. And when the aircraft takes off, the wings go up due to the air pressure. So the aim of this test is to stay well ahead of anyone who's flying this aircraft commercially, and to provide maintenance data. So again, as part of your criteria, I noticed that maintenance and ongoing maintenance is one of the criteria, or part of one of the criteria that you're to consider. This is what that looks like for a full-scale aircraft. It's one of the many tests that they do. So 9 years into my career at Boeing, I was running a production engineering team. Our job was to introduce change into the production system and all of the management associated with that. And I realised the bit of my job I really, really loved was working with people. I'm capable of doing the technical content, but it's not something that I was really passionate about. So I left Boeing and I took up the Director of Operations role at Engineers Without Borders here in Australia. And our focus is all around engineering and how it can make people's lives better. So if you think about where engineering as a career came out of the Industrial Revolution, and it was all about providing access to shelter, water, energy, all the basic necessities that we take for granted every day. And that's what we do, and we're trying to reframe engineering to look at it from a person's perspective. So I thought I'd share what that looks like for us. So this is the design cycle as Engineers Without Borders see it, and I want to focus on two of these criteria particularly. And it's the discovery and the empathise phases, and for you guys that will look like the information you build into your design brief. And discover and empathise are all about who are you designing for and what's appropriate for them in that particular context. So it's about listening to people, it's about understanding that context, And one of the best examples I can give you is the example from one of our partner organisations who was working in Africa. And they identified that respiratory diseases were a big problem for this particular community, particularly for the women and children, and it came from cooking indoors. So the fires inside, lots of smoke, and you end up with high rates of respiratory disease. So there's a solution for that. They're called solar cookers, and they're a big silver cone, if you like, and you cook at the centre of them, and they use solar energy to heat the food. They're very effective, they're cheap, they're easy to distribute. So they've distributed 1,000 of these solar cookers to this particular community. And 6 months later, they came back and they were trying to assess how their implementation had gone, and there was one still in use out of 1,000. They hadn't broken, they were still there. But what they found is that for that particular community, when you cook outdoors and people walk past what you're cooking, it was culturally required that you share what you were cooking. So for a community that had very little food to begin with, people found that they had less food when they cooked outside because they were required to share it with anyone who walked past. And as a result, they were cooking indoors again. So that's really, to me, an example of what empathise looks like and what the discovery phase looks like when you're defining a design brief. Who's going to use it, and is it something they're going to use? What are they going to use it for, and how are they going to use it? So some tangible examples of what that looks like in the work that Engineers Without Borders Australia do. This is an example from our current first year. We run an engineering design challenge for first year students each year. It's run in universities across Australia, New Zealand and the UK. And it's kind of like crowdsourcing engineering solutions, if you like. And these are the design areas that it typically focuses on. To give you an idea of the context, it's always a real-world community. This year, the community is a Zambian community of refugees. They're quite unique in that it's been a refugee community since 1963. It's not a new community. And the Zambian government are doing something which is very unique, which is giving these people citizenship and land. So they're integrating these former refugees into the Zambian community. Really, really exciting project. And what I would take away from this is that we often think of engineering as very linear, and that you study one thing and that's what you go on to work in. My career is obviously an example of that not being quite as linear as people perceive. These design areas are another example. So in this particular community, one of the challenges around food, and again, processing food and cooking are obviously related. Smoke inhalation is a common issue for communities that we work with, such as this. If you remove the smoke inhalation problem in this particular community from the housing, you're also removing their ability to preserve food, because they use the smoke and in the rafters of the homes to preserve food. So there's a flow-on impact there, and that's, again, to me, a really great example of what empathise looks like and what an appropriate design brief looks like in terms of the flow-on impact of the decisions you're making and the way you define the design brief. To put a human face to this particular community, this is Harriet, and she's demonstrating some agricultural techniques here to the team while they were doing the data gathering for this project. Again, agriculture is integrally related in this particular instance to waste management. It's very poor, arid soil. You can see it's very sandy, and in the broader pictures of the community, it looks a lot like, to me, it looks a lot like outback Australia. And so conservation of water and conservation of nutrients is really important. Related to that, there is actually no waste management system in this community. And by no waste management system, I mean no authority that has any governance, if you like, or process around collecting and doing anything with the waste from the community. Again, as an example of not thinking about the people that you're designing for, or the context for which you're designing, the community installed rubbish bins particularly around the market area, because there was a lot of organic waste. Without the whole of system view on that, and I would encourage you to think really broadly about what systems can mean. The rubbish bin's filled up, great, full, no one to empty them. There's no processing in the community, so people stopped using them. So it's another example of where, without taking that whole of context view, there really hasn't been an effective solution. So I'm going to touch on just a couple of these. These are some of the principles that we use when we're looking at design and when we're looking at solutions for a community. And I'm going to start with the sector building approach. So we take a very whole of sector approach to the work we do, and try and make it very long-term sustainable within the community. The other two that I'll touch on are strengths-based and capacity building. So strengths-based is all about what's worked before, and I think that's highly applicable to what you guys will be doing as part of your projects. You don't have to start from scratch. There's a perception in engineering that you have to start from scratch. There's so much good information out there that you can build on and integrate differently and innovate, for want of a less buzzier word, into a context that it hasn't been thought, no one's thought to use it in before. In terms of capacity building, we're also looking at, in terms of our production system design, we look at sharing information with the community so that community is empowered to then take that forward and we can remove ourselves. So our long-term goal is not to remain embedded within any of the communities we work in, and that's what capacity building is all about. So again, a bit of a tangible example for what that process looks like in the real world, in particular here with relation to biogas and biodigesters. So biogas is effectively, predominantly a methane-based product that comes as a result of breaking down organic waste. So it can be human, it can be animal, or it can be agricultural byproduct. This context is Cambodia, and it began with a project on the Lake Tonle Sap in Cambodia, which is a floating community. They have a 8 to 10 metre change in their water level wet to dry season, which is a whole lot of water if you think about it. They didn't have ready access to fuel for cooking, and they also had a huge waste management problem, particularly during the wet season when you couldn't build a conventional toilet. So biodigesters is a project that was started as a first-year engineering design project for our university students. From there it went to a number of different research projects that we ran in conjunction with the universities, then into a 3-year placement where a field volunteer professional engineer spent 3 years in the field refining and testing that solution with the community. And it's now a social enterprise that is fully Cambodian run. We've produced our first production units of this system in the last 2 weeks, and that's what they look like. To give you an idea of the size of the impact that this could have, we believe that the market in Cambodia is about 1 million of these units. There's about 1 million families that would benefit from this technology. The methane gas is used for cooking, and they're able to not have to build pit toilets, which is the common form of latrine. In terms of the design and the design process, and again I'd pick up on the design criteria that you have as part of this subject, this design is still in iteration. So this is now a 6 or 7 year old project in terms of the life cycle of the project, and just last week they determined that they needed to either bury the tanks, or you can see in the top there the sort of dark green frame that they've put into the plastic tank, because the tank itself isn't actually rigid enough when it's full of liquid. So when you're thinking about design and testing, think about it as a process. It's a journey, it's a learning process. It's all about how you document and reflect on that process, not so much what the end outcome is. So I put this in because for me, I think engineering, and certainly we define it too narrowly. We often think about engineering and the boundaries associated with engineering in terms of numbers and hard requirements that are easy to put down on paper. I would challenge you to also think about the physical and the social boundaries some of which I've touched on today. Economic boundaries, is there, if the community you're designing for doesn't have access to a material, or the person you're designing for doesn't have access to that material, is it an appropriate solution? An example of that I was given recently was a small social enterprise that started up in Sydney. A couple of designers got together and thought that they could use 3D printing for something a bit more interesting than what it's typically being used for. It's quite gimmicky. A lot of things are being used for 3D printing. And their passion was in the disability market and in providing people with access to appropriate technology to enable them to live a more normal life. An example they gave in the talk that I heard last week was a gentleman who had severe physical disability and hadn't been able to control his wheelchair in 5 years. So he had a wheelchair, fully mechanised wheelchair that he could sit in. It was quite safe for him, but he could no longer use the controls. He'd been told that the little toggle stick that he needed to do two-finger control on his wheelchair would take up to about 18 months to procure, and it was going to cost $1,800 to buy that little attachment thing. Within about 3 hours, and with about 50 cents worth of plastic, they had printed him a 3D printed solution. So again, an example of how production processes are really changing and how technology can really be used effectively to provide, and the photos of this gentleman driving his wheelchair for the first time in 5 years were pretty amazing. It's fundamentally changing how we think about production processes and who we're designing for. So in terms of where I'd like to go and where my passion personally lies, food security is something that I think is possibly the biggest issue that we're facing in the next 50 years as a planet. The green is obviously where we have secure food and secure supplies of food, although I would argue some parts of Australia that's not true either. And then there's whole big swathes of the world that just don't have access to sufficient food. I think it's a huge challenge. It's a massive systems problem with if you overlay something like this with where our food is produced and how it's transported and how much waste we cause. And that's where my passion lies in the future. But on that note, I'm happy to take any questions. I'll repeat if you want, Susie. Do you want me to repeat the...
On that map you had earlier, there are a bunch of white areas. Are those just areas where there haven't been results taken, or?
Yeah, that's my understanding. Yep.
Brilliant. We got any other questions for Jane? Teachers, got any questions?
What was the solution to the bins filling up with rubbish?
We don't have one yet. It's being designed in as part of the move. So the community is living, the Zambian community I was referring to is currently living in a village. It's quite well established. It's second and third generation now living in the village. As part of the relocation, they're being given land that's about 20 kilometres away from the village. And as part of that, we're designing infrastructure for that, including waste management.
I'm just going to ask some questions that students from the last session asked. Is engineering hard?
I love this question. That's very mean, Susie. I think I found my first couple of years of work much harder than my study, but hard in a different way, hard in a new information way. For me, my degree was 5 years long, although that is changing these days. It seems to change each year. And in terms of the volume of technical information, I did a highly technical degree as well. There was no business or economics subjects or world politics or anything in there, which looking back perhaps would have been a good idea. But yeah, huge amount of technical information, much more than you receive at school, very quickly. So yes, you do have to stay on top of it, but it all depends on what you define as hard and whether or not you enjoy it. For me, it's all about you've got to be doing something you enjoy.
Beautiful, thank you. Are there any more questions at this stage? I'm just going to jump up here. Can we please give Jane Hadjion, Acting CEO, a big round of applause? Thank you. Wonderful presentation.